Hi guys, and welcome back to 7 Steps to a 7 in Olympiad Algebra. In the last video, we started off the series by looking at polynomials and symmetric sums. And in this video, we're going to be looking at inequalities. Now, in the handout accompanying this video, I wrote a very silly introduction with ChatGPT about inequalities. But the point is that Olympiad inequalities on their own are super rare. Like they don't appear very often on contests. And when they do, the ones that do end up appearing are incredibly hard, usually problem 3 or problem 6 level, and are not suitable for our purposes in this series. However, one thing I want to emphasize is that knowing the basics of inequalities is essential for Olympiad algebra because a lot of these problems usually hide the inequalities inside them, and these inequality problems disguise themselves in very weird ways. And again, as I said earlier, the basic steps can be used as intermediate steps inside much longer solutions. So therefore, I'm going to go ahead and allocate Olympiad inequalities to their separate video instead of combining them with another video. But I'm not going to take several videos to discuss Olympiad inequalities. Anyways, without further ado, let's get started. So as it turns out, most of the inequalities we'll be dealing with stem from one very simple fact, that x squared is greater than or equal to 0 for all real numbers x. And this is just true because, well, positive times positive is positive, 0 times 0 is 0, and negative times negative is also positive. So because this inequality is super simple, it is called the trivial inequality. And this actually says a lot because, for example, if we plug in a minus b squared here, then this is a squared minus 2ab plus b squared and greater than or equal to 0. And with that, we arrive at our first non-trivial result. A squared plus b squared is greater than or equal to 2ab. And this is known as something called AMGM, which I'll discuss later. And from this obvious fact that x squared is greater than or equal to 0, we got something out of the blue. And we're wondering how on earth that even worked. But we can do even crazier things with this. For example, we can go ahead and let this one here be x and this one be y, so that x plus y is greater than or equal to 2 squared xy, given that x and y are positive real numbers. Or x plus y over 2 is greater than or equal to square root xy. Now, x plus y over 2 is something very special called the arithmetic mean. While the one over here is called the geometric mean. So what this is basically saying is that the arithmetic mean, AM, is greater than or equal to the geometric mean, GM. In other words, AM is greater than or equal to GM. And this is the simplest case of what is known as the AMGM inequality. And I'm not going to go ahead and state what AMGM is right now, but for now, just note that the two variable case stems from the idea that squares are greater than or equal to 0. Now, before I get into the full statement of AMGM, let's take a quick look at how this trivial fact that squares are non-negative can be used to give us non-trivial results. For example, we have this one here. The sum of the squares on the left-hand side and this sum of squares here over here is greater than or equal to this product here, the sum of them all squared. And this is what is known as the Cauchy-Schwarz inequality. And in fact, Cauchy-Schwarz, as we'll see in a bit, follows directly from the fact that squares are non-negative. Nothing else is needed. So how do we go ahead and start this problem? Well, we want to not deal with n variables right now because that's a bit much. So for now, let's go ahead and deal with n equals 2. Then we get a1 squared plus a2 squared, then b1 squared plus b2 squared, Well, we want to prove it's greater than or equal to a1b1 plus a2b2 all squared. Now, what do we do from here? Well, the 100% error-free way to solve any inequality that you may come across is to just simplify and expand. And literally nothing can go wrong if you simplify and expand. And after all, that is how we derive the two-variable AMGM, right? Anyhow, if you try using any intermediate inequality, there's always going to be a chance that you get busted. You're going to get something that's not true. So let's go ahead and try expanding both sides out. And if we do that, we get like a1 squared b1 squared plus a2 squared b1 squared plus, I think, a1 squared b2 squared plus a2 squared b2 squared is greater than or equal to a1 squared b1 squared plus 2a1 a2 b1 b2 plus a2 squared b2 squared. And these guys cancel out, luckily enough. And so what we end up with is a2 squared plus b1 squared plus a1 squared b2 squared is greater than or equal to 2a1 a2 b1 b2. Now this looks very suspiciously like the trivial inequality or the two variable case of AMGM that we got earlier. So we want to see if this is equal to 2 times a2b1 and a1b2. And luckily enough, it is. And this therefore finishes by the trivial inequality. And I'll have to specify this that all steps are reversible. How come this matters? Well, for example, if I wanted to prove that 1 equals -1, I could square both sides to get 1 equals 1, and then therefore claim that 1 equals -1. So you have to specify that all steps are reversible when you're working backwards like this. Otherwise, you're not going to get a good result. Anyhow, that resolves the n equals 2 case. And from what it seems like, expanding out both sides will do the trick. So let's go ahead and do that now. So this left-hand side becomes a1 squared b1 squared plus a2 squared b1 squared plus so on and so forth plus an squared b1 squared. Then you have a2 squared, or this should be a1 squared b2 squared plus a2 squared b2 squared plus all the way to plus an squared b2 squared plus so on and so forth, and then plus like a1 squared bn squared plus a2 squared bn squared plus all the way to plus an squared bn squared. So this is the left-hand side. And the right-hand side here is equal to, if we expand it out, a1 squared b1 squared plus a2 squared b2 squared plus all the way to plus an squared bn squared. Then we have like 2 times some humongous thing. So we have like a1 a2 b1 b2 plus then a1 a3 b1 b3. And what we actually end up with here is a symmetric sum. And we end up with an minus 1, bn minus 1, an bn. So as I said in the video last time, we could use the symmetric sum idea. And it seems like each component of the symmetric sum will be useful in our computation. Anyhow, just like before, these diagonal terms, in a way, cancel out. So we're getting rid of all these. And what's left is to deal with like a2 squared b1 squared and so on and so forth. Now in the proof of the n equals 2 case of Cauchy-Schwarz, we had to use a2b1 and a1b2 together. And that gave a2 squared b1 squared plus a1 squared b2 squared is greater than or equal to by the AMGM to A1, A2, B1, B2. And that is just this term over here. So what happens if we just repeat this for all the symmetric sums we come across? Well, then we get these two here. I'm going to go ahead and circle them. Gives this one here. Then you have like an A1 squared B3 squared, and then an A3 squared B1 squared. Those get circled together to get this one out of the way. And then we have an an minus 1 squared bn squared, and then an squared bn minus 1 squared. And those get circled together with that. And when we keep circling everything together, we end up getting that the left-hand side is greater than or equal to the right-hand side, and this finishes the proof, because the sum of many, many squares is non-negative. Now let's go ahead and write up our proof. So the way we're going to start off is by starting off with a fact that we know is true. A1b2 minus A2b1 all squared. Then we just do this symmetrically. And this is greater than or equal to 0. And then expanding both sides and bringing all the terms that are negative to the other side, we end up getting a1 squared b2 squared plus a1 squared b3 squared plus so on and so forth. And we end up going over all the I and j which are not equal. So we can actually notate this with sigma notation as I not equal to j, and ai squared bj squared is greater than or equal to 2 times the sum where I is not equal to j of ai, bi, aj, bj. And then we have to add in the a1 squared b1 squared plus a2 squared b2 squared, and so on and so forth, that we canceled out earlier. And that means that when we do that, we can actually get rid of the I. Actually, this should be not, there should not be a 2 there. We can make this I, it can just make this in general I and j. And this should also be in general I and j. And then these end up factoring as we want them. N squared, b1 squared plus all the way to plus bn squared is greater than or equal to a1 b1 plus all the way to plus an bn all squared. And this finishes a proof. So there are a few things that you should take away from the above solution and proof. And the first thing is to work backwards. By working backwards, we can reduce the inequality to something that's much easier to prove if it is true at all. And we'll see a case where an inequality that we want to prove is not true. And then the second thing is when you're writing the solution is to write forward. In other words, start with facts you already know and then build up from there. And then the third thing is that the trivial inequality is incredibly powerful. And I hope that this proof demonstrated. And the fourth thing is to expand. Expanding means you cannot go wrong anywhere. Now, before I continue to AMGM, I want to mention a few brief things. For one, we note that Cauchy-Schwarz here, as I said earlier, is equivalent to the sum of all these squares here being greater than or equal to 0. So when does equality in Cauchy-Schwarz occur? That is, when does a1 squared plus a2 squared plus all the way to plus an squared and b1 squared plus all the way to plus bn squared equal this side here? Well, based on our proof, all of these squares here must be equal to 0. So a1 b2 is equal to a2 b1, and so on and so forth. So in other words, a1 over a2 is equal to b1 over b2. assuming that none of them are equal to 0. And then we have this is true for all the rest. And therefore, we end up getting that equality holds if and only if a1, a2, all the way to an is just a scaled up version of b1, b2, all the way to bn. So just scale up. I hope that this provides the importance of equality cases. And oftentimes in Olympiads, you're going to be faced with equations which are just the equality cases of inequalities. And with those, you end up proving that you have the equality case and you extract the solutions. The second thing I want to bring up is something called homogenization. So suppose that we want to prove something like a squared plus b squared plus c squared is greater than or equal to 3. Well, how do we even prove this? Well, for one, we know that it is not true. Just take a equals 0.1, b equals 0.1, and c equals 0.1. And it's not true. So we really need an extra condition in order to make it work. So we could have an extra condition, suppose a plus b plus c equals 3. And we want to end up proving this. Now, how do we end up solving this problem here? Well, how do we make both sides have degree 2? Because this one has degree 2 and this one has degree 0. So if we had this on our own, then as we saw, we could just take a, b, and c to be incredibly small and make this false. So if we have a valid inequality in a way, both sides have to have the same degree. So what can we multiply this side by to make it not change at all, but still have degree 2? Now here's a kicker. We can go ahead and multiply by a plus b plus c squared, and this here is equal to 9. So we have to end up dividing by 9 again. So this is a plus b plus c squared over 3. And therefore we reduced it to a squared plus b squared plus c squared is greater than or equal to a plus b plus c squared over 3. Now there's something I want to note. This is as strong as our original inequality that we wanted to prove. So as strong. Because really all we did was add this a plus b plus c squared. And when a plus b plus c equals 3, this gives us our solution. And this generalizes to the case where a plus b plus c is not equal to 3, because scaling up both sides doesn't really change the inequality, since you're multiplying by like lambda squared for a scalar, and then lambda squared again for a scalar. So therefore, this inequality that we have here is basically what we want to prove. And now we can go ahead and turn it into 3a squared plus b squared plus c squared is greater than or equal to a plus b plus c squared. And this one here, this looks a lot like Cauchy-Schwarz, and so does this one. So we really want to make this like a times 1 plus b times 1 plus c times 1, because that's like the most natural way to incorporate it. And by Cauchy-Schwarz, we get 1 squared plus 1 squared plus 1 squared. A squared plus b squared plus c squared is greater than or equal to a plus b plus c squared. And this one here is actually equal to 3, and this means that we are done. Now we could have just phrased the argument as follows without even needing to homogenize the equation. We end up getting 1 squared plus 1 squared plus 1 squared, a squared plus b squared plus c squared is greater than or equal to a plus b plus c squared is equal to 9, and we are done. But the thing I don't like about this argument here is that it does not reveal the motivation behind the solution. While when you homogenize it, you end up revealing how to get the solution and demonstrate how the given conditions should get used in the end. And many times, homogenization will have a much bigger role than this, and I'll go ahead and give an example of this at the end of the video. So now we can go ahead and give this full statement of AMGM in all of its glory. I won't be proving it here, but I'm sure you can probably find a proof somewhere online. And it goes as follows. Suppose that a1, a2, all the way to an are positive reals. And they can also be non-negative. They can be 0. Then what AMGM states is that a1 plus a2 plus all the way to plus an over n, their arithmetic mean, is greater than or equal to the nth root of a1, a2 all the way to an, their geometric mean. And this is AMGM. And the important thing to note is that when n equals 2, we end up getting what we had earlier, where the arithmetic mean of two numbers is greater than or equal to the geometric mean of them. And that is basically the trivial inequality. So with AMGM said over here, let's go ahead and solve our first example. That's not a key theorem. And here it is. Suppose that a, b, and c are positive real numbers. What we want to prove is that a cubed plus b cubed plus c cubed is greater than or equal to a squared b plus b squared c plus c squared a. Now, how do we even get started here? Well, for one, we could try using AMGM on this left-hand side. And when we do that, we get a cubed plus b cubed plus c cubed is greater than or equal to 3 cube root of a cubed b cubed c cubed, which is 3abc. So if we could prove that 3abc is greater than or equal to a squared b plus b squared c plus c squared a, then we're done. But we can't really use AMGM over here because we have like one term. And if we try using AMGM over here, we get a squared b plus b squared c plus c squared a is greater than or equal to 3 times the cube root of these two combined to 3, because 2 plus 1. And then we have another 2 plus 1 and then another 1. And that's just 3abc. So instead of proving this, we proved the reverse of what we wanted to prove. So in a way, we have to prove something that's not true. So doesn't that make the inequality false, you may ask? Well, no, it does not. And in fact, this only means that this approach doesn't work. And we just have to try a different approach. So let's go ahead and do that. So let's go ahead and treat each term individually. So a squared and b. And we'd expect this to be the geometric mean part of AMGM. So we have like twice as many a's as we do b's. And because we have an a cubed and b cubed here, we can try doing like a cubed plus b cubed all over 3. Because then we have twice as many a's as we do b's. And this is greater than or equal to the cube root of a 6b cubed, which is equal to a squared b. And then similarly, we get b cubed plus c cubed over 3 is greater than or equal to b squared c, and c cubed plus a cubed over 3 is greater than or equal to c squared a. And when we add them all together, we get this is like 2a cubed that over 3 and a cubed over 3, so that combines to a cubed. And we similarly have these guys, and it's greater than or equal to this over here. And an exercise for you to figure out is, when does equality hold? Because I want you to figure that out on your own. The point is that with this here, we have that we need to do a bit of extra manipulation, and it requires a bit of ingenuity to solve. And I could go on exactly when AMGM could ever work. And there's a neat classification where AMGM can work on either side, given that both sides are symmetric. But I'm not going to go into that in the video because, one, it's incredibly irrelevant, and two, it's not very suitable for our purposes, and it's very complicated. But if you want to search it up, you can go ahead and search up the keyword Muirhead's inequality. Anyway, besides the point, I hope that this example here demonstrated how AMGM has to be used inside very weird ways, and it's not just going to be a direct application. Now, there are a few more things that you'll need to know, but luckily, these things are super intuitive that you'll have no problem remembering them at all. So let's go ahead and discuss the first one, convexity. Now, suppose you have the graph of y equals x squared, and it looks something like this. Now, suppose we choose 3 points on this graph. So we could have like x1, x2, x1 squared, and so on and so forth. And now let's go ahead and take the centroid of those points. And when we do that, we have something like here. This is like the center of mass. And then we have the point right below it. And as we see, the centroid here is always above the blue point that is above. And put into math terms, the y-coordinate of the centroid here, which is going to be, if we let this function be f of x1 plus f of x2 plus f of x3 all over 3 is greater than or equal to the y-coordinate of when the x-coordinate is put into the function. So f of x1 plus x2 plus x3 over 3. And this basically follows because this point here is just always going to be above this one. And in fact, this very intuitive idea can be turned into a more general inequality. So suppose that f is pointed up on an interval I. So in other words, for all x1, x2, x all the way to xn inside this interval, we have that f has that U shape as we had earlier. Then the following inequality holds. F of x1 plus all the way to plus xn over n is less than or equal to f of x1 plus f of x2 plus all the way to plus f of xn over n. And if it's pointed down on the interval, so then it creates some n shape like that, then we'd expect the centroid here to be below it. And therefore, we'd have to flip the inequality sign. Now, this inequality here is known as Jensen's inequality. And it is extremely intuitive if you know what pointed up and pointed down mean. But wait, you may ask, how do we know if a function is pointed up or pointed down? If you know calculus, then the answer is that if f is differentiable, or twice differentiable, it is pointed up on the interval I if f double prime of x is greater than or equal to 0. So that's when we have that it is convex. Convex means it's pointed upwards. So convex. And then concave means pointed down. And this happens if f is twice differentiable, f double prime of x is less than or equal to 0. Now, if you don't know calculus or what a derivative is, then that's okay. Here are some basic functions and whether they are convex or concave. So f of x equals x to the r is convex for r greater than 1. And for x greater than 0. And f of x, and this should be x, f of x equals x to the r is concave when 0 is less than r is less than 1. And then we have f of x is equal to a to the x is convex for all x in the real numbers when a is greater than 0. And finally, we have f of x equals log ax is concave for all x greater than 0. So these are just some very, very common functions. And if you want to know exactly how differentiation works to determine convexity or concavity, I provided a link inside the handout that covers the absolute basics, and it's from a physics perspective, so you don't have to worry about all the nitty-gritty. The other thing you need to know is also very, very intuitive, and it is called the rearrangement inequality. So suppose we have real numbers x1 less than or equal to x2, less than or equal to so on and so forth, less than or equal to xn. And we also have y1, y2, all the way to yn similarly. And suppose we want to mix and match all of them and try maximizing or minimizing the sum. Well, we have x1, we could pair it with y2, then x2 could be paired with yn, and then this one could be paired with that, and so on and so forth. And in the end, we end up getting a sum like x1, y2 plus x2, yn plus x3, y like n minus 5 plus so on and so forth. And then plus like maybe xn, y2, who knows? Or xn, y1. And what is the maximum value this sum can obtain? Well, we'd expect that we can just work greedily, where we can just pair the largest ones with each other and then just keep going down the chain. So we would expect by our intuition that the largest possible sum is x1, y1 plus x2, y2 plus all the way to plus xn, yn. And this intuition is actually correct. And this intuition is called the rearrangement inequality. And it states that if we have the sum from I equals 1 to n of xi, y, then sigma of I, where sigma is a permutation of the numbers 1 through n. So basically, it's our way of indicating the mixing and matching. The best way we can do this is when we have I equals 1 to n and xi, yi. So that's the maximum value it can obtain. So in a way, this is the best case scenario theorem, which is more powerful than you might think. Now, the only place where it seems like the xi are used in order is so that we can mix and match them separately and more easily. However, it actually turns out that we have a form when the xi and the yi are not in order necessarily. And suppose that x1, x2 all the way to xn and y1, y2 all the way to yn are real numbers, not necessarily in increasing or decreasing order. And we want to see the value of the sum I equals 1 to n, xi, y, sigma of I, where again, sigma is our permutation. Then this sum is maximized whenever the lists x1, x2, all the way to xn, and our permuted list y sigma of 1, y sigma of 2, all the way to y sigma of n have the same relative order. And that's the rearrangement inequality. So it's nothing super, super hard, and it's incredibly intuitive. But to see how powerful it can be, let's go ahead and go back to our example from earlier. That is, a cubed plus b cubed plus c cubed is greater than or equal to a squared, b plus b squared c plus c squared a. Now we solved this using AMGM earlier, but if we have the rearrangement inequality in mind, we can go ahead and try splitting these terms here similarly to these ones. And we get like a squared b plus b squared c plus c squared a is less than or equal to a squared a plus b squared b plus c squared c. So we really want to show that we have a rearrangement BCA of a squared b squared c squared, and we can always do better. And to this end, we have like the list a squared b squared c squared, and we also have the list BCA. And we want to show that we want to do this does worse than ABC. But these guys here, we know that they are in the same order. And They're in the same order because all of them are positive, and this should be clear. And therefore, because they're in the same order, mixing and matching these two together gives the maximum value, which is over here. And in particular, the other one here gives a value that's smaller, and that finishes the proof. So rearrangement inequality is super, super powerful, and you should look out for it whenever you can. And one final thing before we go on to our example problem is that if you want to learn more about inequalities, these raw inequalities hardly ever show up on contests anymore, but in this video, I discuss everything you absolutely need to know, as they can hide themselves in random problems. But if you want to learn more about inequalities, go check out Evan Chen's handout, which is linked inside mine. Now let's try out an example problem from the 2009 IMO shortlist. Let A, B, C be positive real numbers such that the sum of their reciprocals is their sum. And we want to prove this identity here shown on screen. So go ahead and pause the video and try the problem out for yourself. And when you're ready to discuss with me, hit the play button. Okay, so hopefully you've tried out the problem on your own. So let's go ahead and do this together. So the first thing that sticks out to us is that we have 2a plus b plus c, a plus 2b plus c, a plus b plus 2c. So it seems like we're singling out on the a, b, and c. And like we're adding a to a plus b plus c, then b to a plus b plus c, then c to a plus b plus c. So we want to do something with a plus b plus c. But the problem is we have this very nasty looking condition here. So we want to somehow deal with that. And the way we end up doing this, and I forgot to mention this explicitly in the video, although I did mention it in the handout, is that homogenization can work backwards, as we'll see in this problem. So anyways, we have this condition here, and this actually rearranges into like a plus b plus c times abc over ab plus bc plus ca is equal to 1 if you do the algebra. And we can actually, because we have degree -2 down here, we can rearrange it into ab plus bc plus ca over abc times a plus b plus c is equal to 1. And therefore, what we can do is multiply both sides by this to get ab plus bc plus ca over abc times a plus b plus c. And now this is basically equivalent to what we had originally, because this one here is degree 2 or -2. This one is also degree -2. And when this is true, we have our desired inequality. So as I said, by homogenizing, we get something that's equivalent, but also provides us motivation to the solution, or much more. Now, here's the key fact. Remember how I said we can use homogenization backwards? Well, remember how we were looking at a plus b plus c plus that other one. So it would be really, really helpful if we set like a plus b plus c to be some fixed value, suppose 1. And if we set a plus b plus c equals 1, we can do this since they're all positive real numbers. Then if it's not equal to 1, then we can just scale back to when it's 1, and then scale right back up to get our desired result in a way. So let's go ahead and assume that a plus b plus c equals 1. So I'm going to go ahead and put that in the corner. And then when we plug this in, we get like 1 over 1 plus a squared plus 1 over 1 plus b squared plus 1 over 1 plus c squared is less than or equal to 3/16 times, now this one is 1, so it's ab plus bc plus ca over abc. And now we want to somehow deal with this one here. Well, remember how we got that ab plus bc plus ca over abc in the first place, because that's just this one over here. And honestly, we could have just done like 1 over a plus 1 over b plus 1 over c over a plus b plus c from the start, and we wouldn't have to deal with that, I guess. But still, we end up getting that this is 1 over 1 plus a squared plus 1 over 1 plus b squared plus 1 over 1 plus c squared is less than or equal to 3/16 times 1 over a plus 1 over b plus 1 over c. Now, here's the key idea. We're going to go ahead and try moving everything to one side, because we have everything is in terms of a over here and in terms of a over here. So it's like we have a function for a. So when we do that, we get like 1 over 1 plus a squared minus 3 over 16a plus then so on and so forth. Similarly for b and c is less than or equal to 0. Now this is incredibly surprising because we have like this function f in terms of a, and we have like f of a plus f of b plus f of c. You want to prove is less than or equal to 0, given that a plus b plus c is 1. Now, this sum of functions here, this should immediately ring a bell because it's just Jensen's inequality. And when we try using Jensen's inequality, we want to prove two things. One, that f is concave, because that's the only way we can get this less than or equal to sign here. And the second thing we want to prove is that f of a plus b plus c over 3 is actually equal to the right-hand side. Now, f of a plus b plus c all over 3 is just f of 1/3. And when we plug it in here, we get like 1 over 1 plus 1/3 squared minus 3 over 16 times 1/3, which is 9/16 minus 9/16, which is 0. So the second concern is checked. So the only thing we need to check now is that the function we defined, 1 over 1 plus a squared minus 3 over 16a, is concave. And you can go ahead and check this if you know calculus by taking the second derivative and doing it. But if you don't know calculus, then I'm just going to say for free that it is concave. And you don't have to worry about it. I'm giving you this fact for free. But the important thing I want you to take away from this problem is how we first homogenized to get rid of this condition here, then dehomogenized to incorporate a plus b plus c equals 1, and then found this function here, which we wanted to prove an inequality about, and this was very suitable for Jensen. And Jensen ends up working out in the end. So I hope this problem introduced how to combine many of these techniques. So again, as usual, I've provided a bunch of exercises in the accompanying handout, which you should go ahead and try on your own. And if you're stuck on any of them, remember to leave a comment on the video describing your progress, and I'm always happy to help you on the right track. So thank you so much for watching this video, and I'll see you guys in the next one.